So construction of K1. Let S be the set of all irreducible elements of K of X. So S is a very big set. Let A be a polynomial ring generated over K by all xp, where P is an element of S. So it is a polynomial ring of a huge number of variables. One variable xp for every P in S. So this is a polynomial algebra, very big polynomial ring. Let I in A be the ideal generated by P of xp for any P in S. So it is an ideal generated by a huge number of elements. By all, right? We take, for any P in S, we take P of xp, and this is one of the generators of our ideal. So what I claim is that I is a proper ideal. Well, indeed. If not, then I can write 1 in A as a sum of lambda I pi of x pi. So these are generators, some generators of I, and these are elements of A, right? So also some crazy polynomials in crazy variables. But the main point is that this sum is finite. If my ideal contains 1, then 1 is a finite A-linear combination of my generators. Okay? Well, take L, a splitting field of the product of all pi from I of 1 to n. So I take my pi and I take the splitting field of the product of, well, all of the family of pi's. If you want, I generate an extension of K by all the roots of all my pi which were irreducible over K. Okay? So let alpha I be a root of pi in K. Then my A is a polynomial ring, and it's very easy to produce a homomorphism of a polynomial algebra to some other algebra. One must just know where one sends the variables, right? So I can produce a homomorphism of K algebras from A to L, just sending xpi to alpha i's. These are just variables. My A is a polynomial algebra, those are variables. and other xp to 0 if p is different from pi. Okay? And if I look at phi of 1 and use this identity, I obtain that it is 0, because each xpi is sent to alpha I, so pi, so phi over pi of xpi is just, what is pi of alpha I, so it is 0, but this cannot happen. Phi of 1 must be equal to 1, not to 0. Okay? So, I is an ideal. Then, you know how to get a field. I hope you know. So, effect, any ideal, any proper ideal in any commutative associative ring with unity is contained in a maximal ideal. Ideal M, and the quotient A by M is a field. So I just can take K1 equal to A by M. And then continue in the same way. To construct K2, K3, Kn, and so forth. Okay? Well, maybe I should give here some comments on this fact. Because some of you know it, some of you don't. And this is very important, and the technique is very important, and will be used in these lectures. So maybe I make some comments on this fact. So, digression. Ideals in a ring. Well, commutative, associative with unity. I told you in the beginning that all our rings will be like this. So any ring, any ideal, proper ideal, is contained in a maximal ideal. This is a consequence of what one calls Zorn's lemma. So let me give you this Zorn's lemma. Consider P not a polynomial anymore, but a partially ordered set. A subset C in P is called a chain if it is totally ordered, that is, for each alpha and beta in C, one has alpha less or equal than beta or beta less or equal than alpha, where less or equal is our order relation. Okay? So, Zorn's lemma says the following thing. If any chain, say, non-empty chain, any non-empty chain in a non-empty P has an upper bound so an element of P which is greater or equal than any element of the chain, that is an M in P such that M is greater or equal than X for any X in C, then P has maximal elements. Okay? I will not, of course, prove this Zorn's lemma, because you certainly have heard that this is the same thing basically as the axiom of choice or a Zermelo theorem. So this is relevant for set theory, foundations of mathematics, not to algebra and Galois theory. But we shall use it to prove that any ideal is contained in a maximal ideal. Now, let P be a set of ideals in A containing I. Well, proper ideals. Proper ideals are not equal to A itself, containing I. This is non-empty. This is non-empty because contains I. And any chain has an upper bound. Any chain I alpha, where alpha is in some set of indices J, has an upper bound. This is just the union of all I alpha. Well, you check that it is an ideal, it is easy. I'll leave it as an exercise. So, our set P has maximal elements. So, P has maximal elements. So, I is contained in M, a maximal ideal. And if we have a maximal ideal, if we take a quotient by a maximal ideal, then this is certainly a field. Well, otherwise it would have some proper ideals. Some A in A by M would generate a proper ideal, and its preimage under the projection from A to A by M would strictly contain M.